What's up, guys? Welcome back to Chemistry Uncovered, episode 6. I hope that wherever you guys are on this world, that this video finds you guys well, and I hope that you guys are having a wonderful March. And without further ado, this week's video is about Lewis structure, right? But before we go into Lewis structure, I kind of want to mention, Chemistry Uncovers in the works of a lab. I know you guys may be asking, when are we going to do our first lab? We are currently in the works. We're currently in the process of creating our first lab, the flame test lab. Essentially, in the flame test lab, as you can see, it's the colors, the different colors you see from this flame test results from when the electrons go from an outside valence shell to a ground state shell, which releases energy because it becomes more stable, right? And when it releases energy, the energy has certain wavelengths, and those different wavelengths of different elements cause different colors, different visible lights. This is one of my favorite labs to do, and I hope that when we show you guys this flame test lab, that you guys have a wonderful time looking at the different colors shown by different elements, such as calcium or sodium. So this week's video is about Lewis structures, right? Now you guys may be asking, what topics is Lewis structures? I'm talking about single atoms, single atoms, the valence. To draw the Lewis structures for a single atom, you have to draw the valence electrons of the atom. For ionic compounds, that's a structure when metal bonds with non-metals. Metals is the left side of the periodic table, and non-metals is the right side of the periodic table, right? And then covalent compounds, which are universally called molecules, that's a structure when two or more non-metals bond. Okay, so kind of start off, for single atoms. Now, you guys may be asking how you draw single atom Lewis structures. For a Lewis structure of a single atom, it's supposed to show the orientation of the valence electrons of the atom. So basically, you put the element name, the element symbol in the center, which is the atomic symbol, and then you put the valence electrons around the circle, as you can see on this right side diagram. You put it around the circle with the X amount of valence electrons the element has, right? Now, the maximum dots that a Lewis structure for a single atom can have is 8, because the outermost shell always has 8 electrons or less. Now, you guys may be asking, for expanded octets, why can't you draw more than 8? Well, for expanded octets, what you do is you count the number of electrons in the outermost end shell, right? The outermost end shell, there's always the S and P orbitals, which we will talk about in quantum chemistry later. But the S and P orbitals, the maximum amount it can hold in total is 8 valence electrons. So that's what you draw in a single atom. Now I have some sample problems for you guys. Now you guys have a paper and a pen with you guys. Please draw you guys can pause this video and draw the Lewis structures for krypton, selenium, nickel, and gallium. Because so pause this video, but right now I'm gonna go forward and show you guys the answers to this. So basically, for krypton has 8 valence electrons, selenium has 6, nickel has 2. Nickel's a transition metal, so it's kind of hard because nickel has a 3d orbital, but since the 2 electrons is most likely to be released from the 4s because it's the outermost shell, then you draw 2 valence electrons for nickel, and then gallium has 3. Right now, I know it might be confusing about nickel transition metals and like the SPDF orbitals, but we're going to talk about that later in quantum chemistry. And then so the next one's ionic compounds, right? Now, how do you draw Lewis structures for ionic compounds? Well, basically, it's a step-by-step process. First of all, the metal donates a valence electron to the metal. As you can see in sodium bromide, the sodium donates its electron to the bromide, right? And then you draw Lewis dot structures for the metal and non-metal. Determine how the metal's valence electrons will be donated to the non-metal. So draw an arrow to determine how the sodium will be donated to the bromide. Draw the Lewis structure after bonding, right? And then you draw the formal charge, right? So the formal charge is basically, since the sodium loses an electron, it's positively charged because an electron is negatively charged. So if you lose a -1, then it becomes positively charged, right? And then you draw the coefficients for number of metals and metals. So let's say it's like a +2 charge and a -1 charge, such as MgBr2. Then you draw 2. Then you write 1 for the coefficient for Mg, and then 2 for the coefficient for Br. Right now, I have some more sample problems. Please pause this video because I'll go ahead and show you guys, reveal the answers. For HCl, you can see that the hydrogen donates 1 electron to the chlorine. For Mg, for magnesium iodide, the magnesium, now this one's interesting because the magnesium donates 1 electron to both iodines, right? So one iodine they get donated 1 electron, but there's a second iodine that gets donated another electron. And to kind of represent those two iodines, as I explained, you draw the number 2. For lithium fluoride, the lithium donates an electron to the fluoride, and then for barium oxide, the barium donates 2 electrons to the oxygen because the oxygen can gain 2 electrons to fulfill the octet rule, right? And then for molecules, last but not least, molecules. Now, molecules is probably the one you guys will be using the most in the chemistry world because they're probably the most, useful in chemistry. And for molecules, basically it's a step-by-step process too. This one's probably the hardest, so you guys have to pay attention. Basically, for molecules, nonmetals share electrons, right? So you draw the Lewis structures of both nonmetals, 2 or more nonmetals, right? Determine how the valence electrons will bond to satisfy the octet rule. Essentially, you have to use the bonding pair, which is the line, the bonding pair, as you can see through the nitrogen. So determine how it will bond to determine the octet rule. And to confirm this, you can use the equation, the total number of valence electrons divided by 2 equals the lone pairs plus bonding pairs. The lone pairs being a pair of these lone pairs on the element that is not bonding, right? And so basically you have to draw in the lone pairs, draw in the line, and confirm the correct structure using the equation as I said over here. So you can see through nitrogen, you first draw the lines, draw the bonding pairs, and then you draw the final Lewis structure. And to confirm the correct Lewis structure, you use the equation, total valence electrons divided by 2 equals lone pairs plus bonding pairs, right? This is kind of a condensed version, and I understand that in your chemistry classes in your high school or college chemistry classes that the molecules you guys have or the ionic compounds you guys have might be harder. So this is kind of like, I understand that this presentation is kind of like an overview, but if you guys have more questions, I can always have a YouTube live where you guys can come in and ask questions about whatever problems you guys have in your classes. And I'll explain thoroughly step-by-step process on how to do them, right? I have some more sample problems for you guys. I have oxygen, water, which is H2O, carbon dioxide, right? Carbon dioxide, which is very abundant, and then chlorine, right? Pause this video again because I'm gonna reveal the answers right now. For oxygen, you have 2 bonding pairs, and then you have in total 4 lone pairs, 2 on each oxygen. For water, you have 2 bonding pairs, 2 lone pairs on the oxygen. Now you may be asking why hydrogen doesn't have any lone pairs. It's because hydrogen is only has one shell, and that one shell can only hold 2 electrons. So this bonding pair, when it shares 2 electrons, it's basically the total amount. It's enough for the hydrogen to become stable, right? And then for carbon dioxide, you have 2 bonding pairs on each oxygen, and 4 lone pairs in total. And then for chlorine, you have 1 bonding pair, and then 6 lone pairs in total, 3 on each chlorine, right? So basically, Lewis structures is to basically place this with separate model of like, this is water, right? To put this in a 2D plane. This is 3D, but Lewis structure helps scientists put the separate models in a 2D plane to draw them, right? Why do I teach Lewis structures? Why do I, do all of this? It's to make the world a better place. The reason why I'm gonna do a flame test lab, the reason why I upload weekly videos is to help you guys feel the passions of chemistry, but more importantly, feel the passions of whatever, STEM related profession you guys want to pursue, or, whatever interests you guys have. Just make the world a better place through those interests. So thank you so much for watching, and peace out.